Good afternoon, everyone. How are we all doing? Well, I mean, except for the it's small but very significant percentage of people who have been affected by our servers at the moment. So before I even get started talking about 1511 or anything, I just want to apologize on behalf of CSE. Something has happened, and when you think about all the stuff that's running in the background of CSE, we've got, thousands of programmers all working on different types of code and different things that we've asked you as lecturers to do. But everything that we ask you to do is kind of, I guess, in a sense for you, it's like experimental. It's doing things you've never done before. So somewhere along the line, mistakes can be made, and they're not anyone's fault, because we expect students to try things. You know how, like, the other day I was like, yeah, I'm just going to use up all the memory and allow the computer to kill my memory. And I said, let's not all do that at once. We don't necessarily put limitations on people to say, nah, you shouldn't do anything weird with the computers, because to learn properly about how computers work, one has to do everything that they can with them. We don't even know if this is why this is a problem, but I'm just assuming that the reason why this hasn't been fixed yet is just the sheer complexity of looking at, several thousand people programming at once and trying to figure out if one of them did something that triggered something strange on one of our servers. And why is it only one of our servers, or one or two of them, that's causing the problem when they're all kind of running the same software? One day, you too might get a chance to be in a position to have to deal with these issues. Or the interesting thing of, like, how do you build, large server infrastructure so it doesn't have these problems? So we're not even just going to, look at this as like a problem that we have to endure in 1511, but I think it's really interesting to look at this as an issue that is potentially in a lot of your futures. Computers are not simple things to use, as we have found out in this subject. We've been using computers a fair bit, and we haven't necessarily got a full understanding of everything that's going on. We have a lot of trust that other people have an understanding, and we're going to trust the poor and overworked computer support group to deal with the issue at the moment. So just to let everyone know, the context is there is something up with VLab at the moment. It's not VLab, it's actually our file servers that are serving your files. So whether you're connected to CSC systems via VLab or via something else, a certain percentage of people, one of the other lecturers looking at the back end of this said that it was around 1% of people, but considering the number of people who have spoken to us about an email to us, 1511 is significantly higher than 1%, but, it's still not everyone, which I'm happy with. Have had a lot of their files disappear. And for some people, this is, your assignment has disappeared. So this is obviously a problem. It's a big issue, and it's not something that that we're going to just allow to ruin the subject for you or anything like that. So we're just going to wait and see. We're going to let the CSG finish what they're doing, get it all sorted out. We'll figure out how much time and how many files people have lost and stuff like that, and then give people enough extensions so that they actually have time to finish what they're doing. I do have I am watching the clock, and I do understand that assignment 2 and the study period for the exam are pretty close to each other at the moment. So if this thing goes on for much longer, then we'll look to make sure that people aren't also disadvantaged for the exam by not having their assignment finished on time and having to just be kind of twiddling their thumbs, waiting for this thing to come back in the next few days. So that's what I want to say is, like, we're not going to leave you in the lurch. We're not going to leave you without help or anything like that. My advice, if you want to, is draw a lot of pictures in the meantime. If you can't access your files, get the theory going exactly for what you're doing really correctly, because that's actually going to speed up your process later when this stuff comes back. And on the flip side, we're still going to give you a full extension for all of the time you've lost, even if you've been working on paper in the meantime. So there's every cloud's got a silver lining. I would prefer if you just had the resources you're supposed to have the whole time. But we're not gonna we're not gonna stop you from thinking about things or going back and, like, going over labs and things like that. Actually, you can't do that either. Yeah, but whatever you can do. So what I'm saying is, if you've lost your files, please don't panic too much. Feel free to send us an email on the CS1511 email address and just let us know that you've had that problem, and that way we'll have a list of exactly who has had that issue, and then we can go back after the fact and back up and like grab your backed up files and things like that and give them back to you when the systems are given the thumbs up that they're going again. So basically we'll do everything that we can to make sure that your kind of time in the course and the marks that you get for the course are going to be the same regardless of this incident. I know it comes at a pretty bad time because it's like full on assignment time at the moment for the whole school, but you know, we do what we can. And you know, I think this is a very good lesson because this is computer science and we're getting into the feel of like what actually happens in computer science. So let's roll on a little bit into the lecture. You're not going to have me that much for this lecture. I've got Tom delivering this lecture today, so it's a fun opportunity, I think, for Tom, who has done a lot of tutorials and he's a very experienced teacher, but he hasn't done this kind of big broadcast lecture thing. But I'll introduce it and then I'll hand over to him in a second. So last lecture, we were looking at abstract data types. So we've sort of looked at abstract data types before. We looked at them in terms of the multi-file projects, and we started doing that in the linked list example, but we didn't actually get deep into the idea of like the complete separation between what is the interface, the header file, and what is the implementation versus the other code that uses it. I can't remember if that actually has a technical term as well, but I don't think it does, because it's kind of like all the other code. So when we looked at that, and we looked at the fact that there were multiple different ways of implementing the stack that we showed, where the main file would not know the difference, and only under certain circumstances could you even detect that there was a difference between the implementations, but you just simply used it. I think that's interesting, because abstraction, that idea, is something that carries on through computer science, and it's actually one of the main ways that we like to set up projects so that we can work in teams on them. So you may find this quite useful in the future of, you know, having one document which is very simple, like the H file is very simple. It doesn't have much code in it, but is really, really clear and exact about what can and can't be done. And then have people working on either side of that. And as long as they both go through that same interface, it works quite well. The H file is not the only way of doing this. We have things called APIs that are used a lot out there in the world, and they'll do that same kind of thing. So today, sorry, just like moderating. Someone was asking questions about assignment 1, and it's just like taking ass something. It's always funny. YouTube tried to moderate it. Okay, so today we're covering recursion. Recursion I find really interesting because it's like, it's an inversion on the way we think programs are executed. I'm not going to talk too much more about this because from here on I'm going to hop over to Tom and let him take over the lecture for the majority of the lecture. So he's going to show you what recursion is, and I'm basically going to hop into chat there, and so I'll be the one just doing the normal moderation, answering the questions and stuff like that, and I'll let Tom talk about what recursion is. But basically it's kind of like inverted programming, where you have functions that call themselves, and they can stack up multiple function calls, and then they will return through this kind of process. But, you know, I think I've said enough. I'll give Tom a chance to talk now. So this is good. Please go easy on Tom. This is his first time lecturing, although I do have full confidence in him because I've seen his teaching in classrooms and stuff like that. But yeah, but if you want to deliver harsh questions, I will be there in the chat to answer them for you. Okay, Tom, I also, hopefully the tech works. It definitely worked the other day when we tested it. So I'm going to stop streaming now. The stream will pause, and then Tom will take over the stream. Okay, Tom, I'm stopping now.
Okay, I'm hoping that we should have just gone live. Yes, I can see myself. All right. Can everybody hear me just to check? See me? Can people hear me? Yes, I'm seeing yeses. All right, awesome. Now, look, the first thing I have to confirm, a rumor that's been going around Yes, this lecture is the beginning of my coup with chicken. We've already taken out the essential infrastructure, and the next step will be that, what was that? Mark's gone. Oh. So, sorry to let you know about that, but I hope you'll enjoy the next 2 hours as we talk about recursion. So, recursion, I've jokingly called it solving problems with your mind, which we may also need some code today as well. But the observation that Mark made when we were having a discussion about this lecture was, and I will change into the right slides, isn't everything solving problems with your mind, says Mark. To which my answer is, well, yes, everything is solving problems with your mind, but recursion is interesting because it's a new way of thinking about how to solve problems. It's not just about we're going to come up with a procedure that we're going to follow that at the end will just magically produce a solution. What we do is we break things down into smaller and smaller parts until we get to a really, really easy problem. We solve it, and then we build back up again. And one of the nice things about recursion is it turns out that this is actually it can create really elegant and really short programs in some circumstances. And so that's what we're going to be looking at today. So let's look at how we've learned to solve problems so far. Let's say that our problem is that we want to take a linked list of positive integers and we want to find the largest number in that linked list. Okay, hopefully this is something that we sort of have a hint about. We sort of kind of seen this before maybe. We're going to initialize a variable called max, and then we're going to initialize it to something small, so -1 in this case. We choose -1 because if it's a list of positive integers, then we know for sure that's smaller than every integer we could possibly choose. And then we're going to loop through each node of the linked list, and if we find that the current value that we're at is bigger than our maximum value, we update the maximum. And this is a perfectly fine way of solving this problem. It's a way of solving this problem that we start at the start of the list, and by the end of the list, we're sure that we found the biggest value in the list. Let's take a look at a sort of worked example of how this happens. Here's a piece of code. We start off setting max equals -1. We go through, we start at the head of the list, and then we sort of step through. We say, well, we found 42, which is bigger than -1, so we update what our maximum value is. We find 17, but 17 is smaller than 42, so we don't worry about it. We get to 100. 100 is bigger than 42, so we update max again. And then we get to 1, which of course we don't really mind about because 100 is bigger than 1, so I've been told. And then we get to the end of the list, we reach null, we return max, and we find max equal to 100. Wonderful. So now we want to look at a new way. A new way, but this way requires one important observation. And this observation seems a little bit obvious, but it's the crucial step that we need to be able to understand how this recursion works, right? Imagine that we've got a linked list with at least one node in it. There are two possibilities. Either the largest number is going to be the first number. The second possibility, the largest number is going to be something other than the first number. Let's take a look at those two cases. So the first case is that the first number is the biggest. In this list, we've got 42, 17, 12, and 1. And clearly here, 42 is the biggest. So this is sort of that first case where the largest number is the number that we're currently at, or in this case, the first number. Here's a very similar list, but I've made one important change. In this list, 120 is the biggest number, and that's not the first element of the list. So we've got these two possibilities. It's either the first element of the list, or it's in the rest. The biggest number is in the rest of the list. Why is that so important? Because we can now break this problem down into a series of smaller steps. We go back to this problem. We can say, well, first of all, let's take a look at the first number. And then we're going to ask ourselves, which is bigger, this number or whatever is the biggest in the rest of the list? And of course, now we have this question of like, well, how do I know what the biggest in the rest of the list is? So we can reduce our problem down, and now we can ask, okay, let's start at 17. Either 17 is the biggest number, or something in the rest of the list is the biggest number. And we'll keep on working through the list, and we're going to eventually, hopefully, end up with the sort of the answer to our question, and we can start building back up to the point where we can finally know what is the largest number in the green section. So we'd know that 120 is the biggest in the rest of the list. And we could then compare it with 42, and we could answer our original question. Is 42 bigger than 120? In this case, no. And therefore, we can return 120. Let's work through an example of that with some code maybe. That might clarify things. Here's a little bit piece of code I've worked through to walk through this sort of logic. The important note here is that on this second line, it turns out that findMax is calling itself. FindMax calls itself with a value of head next. And so we're actually never going to get to the end of this program until we call find max and start again. Let's take a look at what that looks like. We're starting at the number 42. We say int maximum so far equals find max. In this case, what that means is we're going to be at the start of the linked list, and then we call find max on the next element, which means we sort of forget about 42 for a second, and now we're calling find max on this linked list that starts with 17. And so this time we would say, well, okay, what's the maximum here? And again, we ask ourselves the question, okay, what's the maximum of the next part of the list? We step forward again, and we can go through, and now we ask ourselves the same question for the third time. What's the maximum in the rest of the list? Step through. Hold on a second. Here we thought that we were going to get a nice answer. We thought we were going to be able to solve our problem and recursion would be amazing. But we actually run into an issue here. The issue here is that we've just said find max, but when we try and find the maximum of null arrow next, that's going to cause us an error. Here's the error that we'd see if we tried to use that code by itself. The error basically says we've tried to access something that was null because we got to the end of the list and we asked ourselves, what's the maximum of the rest of the list? But, we don't have a rest of the list that we can look at. And so here's the other big insight that we need for recursion. Well, first of all, I'll mention, had we tried to compile that code, we probably would have gotten an error. Here's the error we would have gotten, and it says all paths to this function will call itself, and this is something called infinite recursion, which sounds really fun, sounds like something you'd hear in a science fiction movie, but unfortunately in this case it will just crash our program. So what's the problem? When we got to the end of the list, when we wanted to get to the point where we had a really simple problem to solve, we didn't actually solve the simplest version of this problem. What we did was we just kept going, assuming that we could always break our list down into smaller and smaller and smaller parts. And that's not enough. So what we need is one extra thing. We need this idea of a base case, is what we call it, which is when we say, well, we've broken our problem down into a smaller and smaller and smaller section until we get to a point where the problem can't be broken down any further. In this case, the problem can't be broken down any further when we end up with an empty list. If our list is empty, in other words, if the pointer is null, then we're not going to be able to return the rest of the list, but we do know something about our list. We know that there's no numbers in there, so we can return something like -1 to say there's actually no biggest number. Or in this case, it's sort of like a flag value telling us, hey, we didn't actually find anything in this list. And what that means is we've broken our way all the way down to the simplest problem being what's the biggest number in this empty list, and now we can start building back up again. Let's take a look at how that works. So as we can see here, the steps that we're going to take is we're going to, once again, break our problem down. We're going to start with 4 nodes, break it down into 3 nodes, then 2 nodes, then 1 node, and then we're going to break it down into the empty list. When we get to an empty list, we return -1, which is basically our way of saying, hey, we've ended up with an empty list and there's actually no biggest element. But then, if we know that our options are, well, either there's an empty there's no elements, or 1 element in our list, with a 1 element list, we're pretty sure that that's going to be the biggest element. And so we can start working our way back out again. Let's take a look at how that works in practice. So, same as before. We've started off with our linked list. Our linked list, we're going to start at 42. And you'll note here that the first piece of code that we've got is not actually our find max piece of code, but we've skipped over this head equals null check. This is the extra special secret sauce that makes our recursion work. It's what we call the base case, and this is what means that we don't keep trying to subdivide our problem forever. It just means that we end up with a sort of smallest problem that we can then start building back out from. Let's take a look at how this works. So, clearly head is not equal to null here. We're pointing at 42. And so we're going to try and find the maximum of the rest of the list. Once again, the exact same situation. We're going to try and break this down even further. This problem's too complicated. We're going to make it even smaller. We keep moving forward, keep moving through the list until when we get to the end of our linked list, now we're asking ourselves the question, what is the largest value in an empty list? And here, the problem is, if it's null, then there are no elements in the list, and therefore there is no maximum. In other words, we're going to return -1. This is just to let us know this list is empty, there's nothing in this list, and so there's no maximum. But now that we know that in the rest of the list there's no elements, when we move back out again, when we sort of say, well, now we know the answer to our question of what was the biggest element in an empty list, now we're dealing with a list with one element in it. And when there's one element in the list, it's much easier for us to be able to say, well, either the maximum is going to be 1 or it's going to be nothing. So in this case, it's going to be 1. And so we've solved our problem of what's the largest element in this one node linked list. And then we take another step back and we say, well, now we've answered our question of what the largest node was in the rest of our list. And we can ask ourselves again, what's the maximum in this new list? In this list that starts with 100 and then goes to 1. In this case, the answer is 100 is bigger than whatever the maximum was in the rest of the list. So in this case, 100 is the biggest node. We've answered our question, we can take a step back again. And this time we can say, well, I've added 17 to the front of my list. And so this time I'm wondering, what's the biggest element in this list? Is it either going to be 17, or is it going to be the biggest element in the rest of the list? In other words, 100. And clearly we can see the answer to that is, well, 100 is going to be bigger than 17. So the biggest element in this linked list is going to be 100. And then we finally take a step back again, and we say, okay, now I'm back to my original list. My question at the start of this whole thing was, what's bigger, 42 or whatever's the biggest in the rest of the list? And for us, we can see, well, if the biggest in the rest of the list is 100, then 100 is going to be the biggest in this entire list. And that's how we can calculate the same thing. So to be clear, what's happened here is that instead of just stepping through once and trying to end up at the end of the list with an answer, we've tried to break down this problem into smaller and smaller sets. We've turned a 4-element linked list into a 3-element linked list, then to a 2-element linked list, and then a 1-element linked list. And finally, we ended up with a linked list that's so simple we could tell what the answer was straight away. We knew that if we had an empty list, well, then there's no biggest element. But once we knew that we had an empty list, we could start building back up again. And we could say, well, now let's start with a 1-element list again. Clearly, in a 1-element list, the biggest thing is always going to be that element. So in this case, it was 1. And then we built back out again and said, well, it's either 100 or 1. And in this case, it was 100. And then we stepped out again and asked about 17. And then we stepped out again and asked about 42. Let's take a look at what this looks like when we're doing some code, when we're using real code rather than just a diagram. I will Alt-Tab into... I'll try and get this to work. VLab. There we go. So, I've just taken this piece of code from a lab exercise and I've modified it slightly so that it's using the problem that we're using here, which is find maximum. And so, if we take a look at this piece of code here, it's the sort of iterative or the normal approach that we've already seen for how to find the biggest value in a linked list. We've defined ourselves an int max, that is the largest element in this linked list. We've then sort of got a current node, which is the biggest, which is the current node that we're at. And then we have this while loop, which goes through and says, well, while we're not at null, while we're not at the end of the list, keep going through. And if our maximum is smaller than our current value, that is, if we've found a new element that might be bigger than whatever the maximum we know about so far is, then we're going to set the maximum element to be equal to that value. And then we keep stepping through the list. We go through the list a few more times. By the end of the list, hopefully we've found the biggest element and we return it. So let's comment out this piece of code now. And we're going to write the same function again, but we're going to write it in a recursive way. I'm using these /* comment style here, which just comments out an entire block of code rather than needing to put a / on the beginning of each line. So let's copy this here. And we're going to get rid of the body of this code. So let's have a think through the steps that we're going to need to take to find our maximum. Well, first of all, as we said at the start of the lecture, we're going to need to be able to break this down into a smaller problem. So at some point, we're going to need to call find max on some smaller problem than finding the maximum of this linked list. In other words, we're going to need to find the maximum of the rest of the linked list, of everything after the current node. Then we're going to need to do some comparison of the current node versus whatever the biggest node we found so far is. the list. And as we noticed when we walk through that first example, we're also going to need to make sure that if we end up at the end of the list, deal with an empty list. So these are the 3 steps that we're going to deal with. And these are 3 steps that often come up when we're dealing with recursive functions. It's similar with other operations we might take a look at later today. It's always going to be a sort of step of we need to make sure that we're dealing with an empty list or with some base case, some simple case. We're going to have to make sure that we call our recursive function. This function calls itself. And then we do some logic to see, well, with the answer to our smaller problem, what's the answer to our slightly bigger problem? So to deal with our empty list, let's write that out. If head is equal to null, if head is equal to null, then we've got an empty list, and we've agreed that the what we're going to use for an empty list is -1. In other words, we're going to use a number that is so small, it's smaller than anything we could possibly find in this list. So return -1. And that deals with already one case. We've dealt with the case of somebody asks us to find the maximum number in a empty linked list. Now let's take a look at what happens if we haven't got an empty linked list, if we've got something in our linked list. Well, then what we're going to need to do is break our problem down further. It's too difficult to solve with a long list, so we want to make our list shorter. What we're going to do is we're going to make a variable called int maximum so far, and we're going to say, well, let's find the maximum value of whatever's after the current node. So head next. And maybe we're at the last node, so maybe this will be -1, or maybe we're going to need to break down this list even further. Finally, we can sort of imagine that we've gone through this process a few times. We've tried to find the max of a smaller and a smaller and a smaller list. We've gotten to -1, which is the empty list. And now we need to deal with sort of building back up again, going from our answer to our small problem to our answer to a slightly bigger problem. And in this case, we're going to ask ourselves, well, is head value, that is the value of the node that we're currently at the start of this list, is that bigger or smaller than whatever the maximum was of the rest of the list? So let's take a look at that. So if the value of the current node is bigger than whatever the maximum of the rest of the list was, maximum so far, well then we're going to need to update what our maximum so far was. This equals head value. And this is because if we found a new node that's bigger than everything else in to the end of the linked list, then that's going to be the biggest node in our linked list, or in the linked list from this point. Finally, we're going to return whatever the maximum was that we found. Because let's say that we had a linked list with one element in it. We've just figured out what the maximum was for this one element linked list. Now we want to find out, maybe I've been called by a 2-element linked list, and we need to tell that linked list what the value was that we found in our little problem. And so let's run this code now and see if it works. Just make this a bit bigger. Unfortunately, the files getting removed wiped my size, appearance, monospace, up to 18. There we go. So let's compile this program. DCC recursion .c-o recursion. I'll do it the other way around, sorry. -o recursion, recursion.c. Program compiled just fine. We can run recursion. We specify the linked list that we're giving it on the command line. So I can say 1, 2, 3, 4, 5. And it tells us the maximum in the list is 5. Okay, that was kind of fun, but let's dig into it a little bit deeper. One of the things that is really interesting to observe about how this recursive problem works is how it's very slightly different to a while loop in how it deals with the problem, how it walks through the problem. How I'm going to demonstrate that is I'm going to put a printf at the start of my function, printf up here called, which says starting to solve the linked list with value %d, and we're going to say head value, and we're going to copy this and put it almost down the bottom. And we're going to say finished solving the linked list with value %d. Can anyone see an issue with what I've done right now? You may be able to notice that accidentally I've put this before my if statement. And because it's before my if statement, I could be calling this printf with a head that's null. So we do need to make sure that this is below our if statement. Like so. Let's rerun our program now and see what happens when we've written our code this way. So we're going to go /recursion 1, 2, 3, or 4, 5 again. Oh, I might put some new lines in there as well, just to make it a bit easier to read. \n and a \n there. We'll save this. We'll recompile again. And what we notice is that we've started to solve linked list with value 1, and then we've broken it down, we've broken it down, we've broken it down, we've broken it down, until we got to the linked list that was of size 1. We went a little bit further, we dealt with the fact that we eventually had an empty list, and we've started to build it back up again. We've said, okay, well now I'm solving the linked list with value 5, and then 4, and then 3, and then 2, and then 1. And this is the big idea of recursion. It's going from something big, breaking it down into smaller steps, dealing with the simplest possible case, and then bringing it back out again. And we end up solving the whole problem because we've managed to solve smaller sub-problems. I want to contrast what that's like to the solution that we had previously, which was the solution with a while loop in it. Let's take a look at that. So here's a solution with a while loop in it. Let's now put in the same comments again. We'll copy this in at the end of the while loop. We'll put it here. And we'll put this one here. Started solving the linked list with value %d. Let's try again and see what happens this time. Run /recursion again. Oh. What have I done? Oh, I've got an interesting bug here. This is something we might focus on a little bit later. So at the moment, we've said solving the linked list with value 1, 1, 1, 1, 1, 1, 1. And unfortunately, it's because I've used head value, not cur value. So in this example, head never changes. The list is always the same. We're just working through it. In the recursive example, our head was always getting smaller. We were making smaller and smaller and smaller lists, and then we were sort of stepping back out again. So let's change this up so it says cur now. So we're looking at where we currently are in the list. And what we notice is that in this method of solving the problem, we're solving one step at a time. We start with value 1, and then we finish with value 1. Then we start with value 2 and we finish with value 2. And then 3, 3, 4, 4, and 5, 5. And so these are two different sort of methods of solving the exact same problem, but one of them works by sort of solving smaller and smaller sets and then jumping back out again, whereas the other one works through things by stepping through. By the end of the linked list with the while loop solution, we've got a solution. That is, at the end of us going through our while loop, we have an answer to the problem. But when we're dealing with the recursive solution to this problem, we actually have to solve smaller and smaller problems, and then we use those smaller solutions to build back out to bigger solutions again. Okay, so I'm going to jump back to the lecture slides again, because I want to look into this example in a little bit with diagrams as well, just to maybe show it off in a different way. Let's just go in here. Go to slides. Okay, so as we've been speaking about for the last few moments, a normal while loop solves your problem by just taking steps, and it solves this first part of the problem and it keeps stepping through. Recursion solves your problem by solving almost a stack of problems. It starts with a big problem, and then it builds it up into smaller and smaller and smaller problems that it can then solve again. Here's a diagram which might give a sort of visual representation of how that works. Imagine that we're about to call our findMax function on this linked list. When I call findMax the first time, 42 is at the head of the list. And in terms of our function, function calls, main has called findMax. And so you can imagine it like a stack where findMax is on top of main. That is, findMax is going to finish before main finishes. So we've started off with calling findMax. Let's now take another step forward, and we're going to look at now findMax, which had 42 at the start of the list, calling findMax again, but this time with 17 at the head of the list. So we can put this on top of our stack as well. And so what we're going to notice is each time we call findMax, we add another part to our stack. We add, in this case, we're adding another findMax that has 100 at the start of the list. And then we're going to add another findMax on top, which has 1 at the start of the list. And by the end, we get to a findMax where null is at the head of the list. And if we remember back to our code from earlier, we remember that if findMax gets null as its list, in other words, if findMax gets an empty list, then what we're supposed to do is we're just supposed to return -1. -1 being our signal that this is there's nothing in this list, and a -1 is smaller than any possible value that could be in this list, given that this list is all positive integers. So we can now take a step back again. We take a step back and we say, well, okay, we've solved our problem when we've got an empty list. So let's now use that to solve our problem when 1 is at the head of the list. In this case, 1 is at the head of the list. The maximum so far is going to be 1, because clearly if there's only one element in the linked list, then 1 is going to be the biggest element of that linked list. And then we sort of solve our problem again. We take another step. We say we finish with what we were just doing. And now we return to our question of, well, what's the biggest element in the list that starts with 100? And so we can solve that problem as well. We know that the answer here is 100. And so now that we've found that answer, we can step back again. And we say, well, okay, now what's the smallest, what's the largest value in this linked list? Is it either the biggest value that we found so far, which is 100, or is it 17? And we can all see that in this case, 100 is the bigger value. And so we've solved that problem. And we take another thing off our stack. And now we return to our original question, which is, what's the largest value in this linked list with 4 elements in it? And in this case, we can see, well, it's either going to be 42 or it's 100. Given that 100 is bigger than 42, 100 is the largest element in this linked list. And we return back to our main function. So this is the basis of how recursion works. We've taken a big problem. We've broken it down into smaller problems. It's worked almost like a stack in the sense of we started with something big and we've broken it down into smaller problems, which we've put on top of our stack again. And then as we've solved problems, we've taken them off the stack again. We solved the smallest problem and we then built it back out into larger and larger problems. I might just take a moment now to have a look at the chat to check if there's anything I need to answer. There's been some good discussion here, and thankfully I haven't lost all my files yet. Okay. So I had break time scheduled for now. We might actually take a look at one more problem before we jump into the break, which was, I'm going to jump back to VLab now. Okay, so we've dealt with this problem of finding the largest number in a linked list. So finding the maximum value in a linked list. But of course, recursion isn't just used for solving problems involving maximum numbers, involving finding the biggest number in a linked list. It can be used for lots of things. The next thing I wanted to demonstrate was how it's not just find max that we can update to use recursion. We can even do printing out an entire list using recursion. Let's first of all take a look at some of the differences that we're about to encounter. First of all, note that while find max returned an integer, printing a linked list is just going to return void. So there's no need for us to do any returning in this problem. Second of all, unlike in find max, where we didn't really need to print anything, print list is actually going to need to print something. So let's comment out what we've got here for print list. And we're going to do the same thing we did before. We'll first of all step through sort of the theoretical idea of how are we going to solve this problem. How are we going to solve this problem recursively? Well, step one, in fact, step 0, as we said above, was what's the simplest case? In this case, once again, the simplest case is going to be dealing with an empty list. And so if we're going to match the format that we had previously, in fact, let's take a look at the behavior of how this function works before we even modify it. So we'll go back to what we already had, and we'll call, we'll go down to our main function here, and we will print out our list. So we'll call print list on head, and we'll say something like printf our linked list looks like new line here. Let's take a look at what this function does when we've written it just with a regular while loop. We'll wait for it to compile. So normally what it does is it prints out our linked list looks like 1, arrow 2, arrow 3, arrow 4, arrow 5, and then an X at the end. So it represents the null pointer at the end of our linked list. Let's take a look now at how this function is written. So we start off with this star n, this current node. While we're not at the end of this linked list, we're going to print out a value, and then as long as we're not right at the end of the linked list, we're going to print out an arrow. And then we step to the next element in the linked list. Once again, this is this approach that we've seen before, where we say we're going to print out the first thing, and then we're going to print out an arrow, and then we're going to step through the next element in the linked list, and we're going to print that out, and we're going to get to an arrow, and then we're going to keep stepping through the linked list. And by the time we're at the end of the while loop, we've finished with our whole problem. But in this recursive approach, which we'll go back to now, in this recursive approach, we're going to deal with it by breaking it down into smaller problems. So like we asked before, what's the simplest case? Well, the simplest case is with an empty list. And so let's write out what that would look like. That's if head equals null. And in this case, what we're going to do is we're going to printf an X, because we're at the end of the list. So we're going to printf an X like we did right at the end of our print list function previously. So we've dealt with this simplest case. We've dealt with this case where we have a linked list with no elements in it. We just print out X straight away. The next question is, let's step 1. What we did last time was we said, well, let's call print list to solve our smaller problem. And the second step that we were going to do was to contribute to the bigger problem of printing out this bigger list. So in this case, we would do print out our current value. Now, this is what we did last time, but for the purposes of this example, I'm going to switch these around for a moment. And what we're going to see in a moment is why switching them around was so important. But let's just start by switching them around. So we're going to print out our current value, and then we're going to solve our smaller problem. So we're sort of solving, we're saying the way that we print out our list is we print out the current thing, and then we print out the rest of the list. Let's have a look at what that looks like. Here we're going to print out %d, and with head value. And then we're going to say, well, if head, or head next, is not equal to null, then we're also going to print out an arrow. I'll put spaces around that arrow as well. And finally, what we're going to do is we're going to call print list to solve our smaller problem. So we've dealt with this bigger problem of printing out the current element. We're going to break it down into a smaller problem now of printing out the rest of the list. Print list of head next. Okay. And see, we just translated our while loop into a recursive system, or into a recursive solution. And this took only these 3 steps. Step 1, we dealt with the simplest case of what happens if the list is empty. Step 2, we worked on the current problem, which was printing out our current value. And then we said, well, let's just deal with printing out everything else. So we called print list head next. And let's take a look at what this does when we compile it. Oh, uh-oh. We've just seen that same error that we saw a second ago. Let's take a look at it. On line 54, it says all paths through this function will call itself. Ooh. Have I forgotten something? Well, let's have a look. So let's say that we've got a 1-element linked list. Let's say our element 1-element linked list is 1, and then go to x. I call print list with head is equal to this node 1, and I step through and I say, well, head is not null, and then I print out our current value. Our current value is head value, which is 1, and then I'm not going to print out an arrow because I'm at the last element. And then I call print list next. And so print list next. Uh-oh. People are telling me he's behind you. This is scary. I understand now, Mark, why you get so scared when people say, oh, he's behind you. Now we're dealing with this new list, which just has x in it. We say head equals null. Printf x. Uh-oh. The next step here is that I'm just going to go back down and I'm going to call printf again. And so here's a problem where we actually needed to return something. We should have said either return here, which will actually escape from this function and finish off this sort of empty case, or what's probably better practice is to say else here. So there are 2 possibilities. Either I've got an empty list, in which case we print out an x. Otherwise, we print out the current value, and then we print out the rest of the list. And it's important to note here that what we've done is we've actually said, well, in one of these cases, we're going to recursively call. So we're going to call print list. We're going to go into a smaller list, and we're going to print that out. In this other case, though, we don't call print list. So in this simple case, we're only just doing something once, and we're not trying to solve any smaller problems. And because we've got this special case here, because we've got this base case, we're not going to recurse infinitely. We're only going to recurse until we get to head equals null, and then we're going to start going back out again. So let's see what that does in the terminal. Oop. He's behind you. I didn't save. TCC. And there we go. And now I can run /recursion 1, 2, 3, 4, 5. And the same as before, our linked list is 1, 2, 3, 4, and 5. But interestingly, this time we were using the recursive solution. So the recursive solution and the while loop solution produced the exact same result, but we just achieved them in slightly different ways. I might comment out the find max code for the moment, just so that we can see it in all its glory. And we'll run it one more time. Look at that. We've got a linked list that we've printed out recursively. So how did we do this? We tried to print out this big list, and we said, well, printing out this big list involves printing out this first element, and then it involves printing out the rest of the list. So we called print list again, but this time with this smaller list. And then we said, well, we're going to print out the second element, and then we're going to print out the rest of the list again. So we printed out elements 3, 4, and 5. And so we printed out element 2, and so we called print list with elements 3, 4, and 5. Then we tried to print out element 3, which we did, and called print list on elements 4 and 5. Then we printed out element 4 and called print list on just this 5. And then we printed out element 5 and called print list with this null pointer. And when we called it with null, it printed out an X, and then it worked its way back out again. It sort of finished up printing 5, said, I'm done printing 4, I'm done printing 3, I'm done printing 2, I'm done printing 1, and we've finished our problem. Okay. I'm just going to check the chat again, make sure I haven't missed anything important. There's an interesting question there, which is when are recursive solutions more beneficial? So the problems that we've seen so far are pretty much the same whether you do them recursively or whether you do them with a while loop. And that's sort of what I wanted the first half of this lecture to be, to just sort of go through how they're basically the same thing. You can solve any recursive problem with a while loop, and you can solve any while loop problem with recursion. In some cases, one of them will be much easier than the other, but you could theoretically solve both problems with either problem with both. But what we're going to look at in the second half of the lecture is a bunch of examples of pieces of code that are much easier to write recursively than they are to write them with a while loop. I think Mark's given a hint there already, which is you're going backwards through something. So we're going to take a look at what it looks like if we wanted to print our linked list out backwards, and we're going to compare that code to printing out our linked list forwards. Let's check if there are any other questions. People noticed that I had forgotten to return in that first case. Okay. Alrighty. What I might do now, we'll go into a break a little bit earlier than usual, and then we'll jump into a sort of larger example, and we should have time to get through the 3 examples that I was planning to get through in the second half of this lecture. So the second half of this lecture should be a good chunk of coding. If there are any other questions, please feel free to ask them in chat, and we can go through them when we come back from the break. But for the moment, I did want to let me jump into a different tab. I'll jump back into my slides. So, break time. It's interesting to look at why recursion is so awesome, and I wanted to give you a bit of a sort of look into where it gets used a lot more than what we've seen right here. So, recursion is sometimes used in the C language. It's very powerful, and it can make some really nice solutions to problems. We've already seen 2 problems that we could solve recursively, and we ended up with some nice behavior, and we ended up with some nice programs, and we ended up sort of understanding our problems in a different way. We had this new perspective of, oh, our recursive problems could be broken up into smaller and smaller things. But it turns out that functions are so powerful, and it seems I've lost a few words there. Functions are incredibly powerful. They're so powerful that they can do anything that a while loop can do. That's what that should say there. So it turns out even that functions are so powerful we don't even need variables at all. We can use functions and never modify our variables at all. You'll notice that unlike in our... I might go back to VLab for a second just to show it off. Go into VLab. If we jump into VLab, you'll notice that whereas in our print list function here, we did a bunch of modifying variables. We said n equals n next, and we had to... let me find the other example. Up here, we had to set this max, and we changed max a bunch of times, and we said, well, maybe max is going to change values. In the recursive solutions, we never had to change variables at all. All we did was we said, well, we're going to... Let me find print list here. We'll jump up here. Cool. So we said... I'll turn on syntax highlighting. All we wanted to do was find this sort of constant value, this value of whatever the solution to the smaller problem was, and then we did some comparisons, and then we could return. We didn't actually need to, really we didn't need to change any variables at all. had we used returning inside of this if statement as well, which isn't good C practice, but sometimes is okay in other languages, we could have gotten away with never setting any variables at all. And that's so useful because using variables in programs can cause a lot of bugs. It turns out that changing variables causes bugs all the time. And it's a common cause of our bugs. Whereas if we have functions and we never change our variables at all, we can sometimes avoid whole classes of bugs that we have where maybe you've forgotten to increment something, or maybe you've forgotten to set something to the right variable. So there's this idea of functional programming, which we don't cover too much in COMP1511, but which you can actually, there are other languages that use recursion to extreme levels that we can't even do in C. And it turns out the most common example of functional programming, actually, I'll ask the chat, can anyone think of the most common example of functional programming that they have seen? It's not going to be something, if you know programming languages, you don't need to know any programming languages to answer this question. Can anyone think of really, really common language that uses functions? People saying Scratch. Definitely Scratch uses some functions, but even more common than that. I would wager that your parents know this programming language. In fact, your grandparents might even know this programming language. Can anyone think of it? Python? Oh, you may have some very, very, very technically minded grandparents then. Haskell, English, HTML, lots of good guesses. The answer? Microsoft Excel. You can think about formulas in Microsoft Excel as calling a bunch of functions on each other. One function calls another function, which calls another function, and there's no such thing as a variable in Microsoft Excel. There are just functions and values. So this isn't too important for COMP1511. We're not going to be testing you on your Excel skills. But it turns out that Excel is an example of this whole idea of functional programming, which recursion is just sort of a toe step into. So I just wanted to mention that, something interesting about how computers work and something interesting about how programming languages work. We're going to take a break now until 5:01. So I will see you all in 4 minutes time. And you may notice that I've stolen an idea from Mark here. This is Katya and Mishka, who are the course admins in charge of COMP1511. I'll leave you to look at them for the next 4 minutes. Alrighty. And I think we should be back now. Let me just check that everybody can still hear and see me. This newfangled streaming thing. Crazy. All the kids are doing it, I'm told. Okay, looks like I am indeed back. Perfect. Thank you, Mark. So, we can get rid of Excel for a second. What I want to do for the next 10 or 15 minutes or so is I'm going to jump into a slightly different view, which is I'm going to draw some diagrams. And the reason I want to do this is because I want to just sort of step through the process of recursion using something other than sort of my hands or a diagram. And we'll see, I'm hoping that if you've sort of been a bit confused by recursion, you've had a few minutes break, you can sort of sit down for a moment, you can think about it from a new perspective, from a new way of thinking about it. So, I'm going to jump over to the side onto my tablet where I can do some drawing. And the first thing that we're going to do is we're going to draw ourselves out our linked list once again. So let me draw myself out a linked list with 1, 4, and 7. So for this problem, let's stick with the idea that we had at the start of an hour ago, with the idea of finding the maximum value in this linked list. Just by looking at it, we can tell that the maximum value in this linked list is 7 here. So the question is, well, how do we find out what this maximum value is? So first of all, we recognize that looking at this big list, it's too long for us to just be able to look at it and say, yep, that's the biggest value. A program wouldn't be able to do that. A program, we can't just write code that looks at it and says that's the smallest value. But what we can do is we can break this problem down. We can break this problem down into, it's either 1, the biggest value is either 1, or it's something over here. Not sure what, but it's something over there. And so what we can do is we can say, well, let's call find maximum with this whole list, but find maximum is then going to break this down further and now ask a smaller question. And the smaller question is, I'll change colors, what's the maximum in this list? So we're going to forget about 1 for a second. We're going to forget that we've seen 1, and we're just going to deal with this smaller problem of what's the maximum in this list of 4, which goes to 7, which goes to null. What's the maximum here? And again, we make the same observation. There's too many nodes in this linked list. We can't just simply solve this problem. We need more information. And so once again, we can break this down into a smaller problem. This time, we're going to say, well, it's either going to be that 4 is the biggest element, or it's something in the rest of the list is the biggest element. And so, once again, even this is too big a problem. We've got 1 node here. Too many nodes. Too many nodes. So once again, we break it down into a smaller problem. And we say, well, I've got this 7, which goes to null. And now we can say, well, either the biggest element is 4, or it's whatever's in the rest of this list. We break that problem down. We now say, well, it's either going to be 7, or whatever is in the rest of the list. And finally, we've reached a point where we have a problem that is small enough that we can solve it trivially. We can solve it without needing to think about it too much. In this case, the solution is, well, if there's nothing at the end of the list, we're going to say -1, or in other words, it's just an empty list. There's no values in it. And given the choice between -1 and 7, we know which one's the biggest. 7's the biggest. And that's a comparison our computer can do. Our computer can say, yes, well, 7 is bigger than -1. So clearly, our computer finally knows the answer to that smaller question of what is the biggest node in, I'll highlight the list here. In this list here. We know the answer. The answer is that in this list here, 7 is the biggest element. And so now we can work backwards. And we can say, well, we know what the biggest element in the linked list at the starting at 7 is. It's 7. So we sort of walk backwards. We say, Okay, let's now try and answer our earlier question of what's the biggest element in this linked list? And in this linked list, it's either going to be the biggest element from this point forwards, which would be 7, or it's going to be 4. And so then we say, well, which is bigger, 7 or 4? And the answer is, well, in this case, 7's bigger. So now we know the answer to a slightly bigger problem. We know that the answer to the question of what's the biggest element in this larger list, in this sort of yellow list, the answer to that is 7. Okay, so we've now just discovered the answer to a slightly larger problem. We know that starting from 4, going to 7, and going to null, the biggest element in that linked list is 7. And so let's now ask ourselves the final biggest question, which is what we started with. The question we started with was, well, what's the biggest element in this entire linked list? And I'll change colors again. We'll go back to here. In this entire linked list, what's the biggest element? And the answer is, the biggest element is either the biggest element of this smaller list, which would be 7, or it's going to be 1. And once again, we look at this and we say, well, pretty clearly, if it's either 7 or 1, 7 is bigger than 1. And so we get rid of this. And we can say that the biggest element in this entire linked list is 7. We've solved the whole problem. So this is that's the process that we followed with the code that we wrote before the break. The process was, we started with a large linked list. We broke it down slightly into a smaller and smaller and smaller linked list until we ended up at the X, and then we worked our way back out again. Now, there's a great question in the chat, which is, what's the point of going backwards to find the biggest number? Great question. So if we started with a big question, which was, what's the biggest number in the entire linked list? And the only way we could answer that question was to answer the smaller question, then what we're doing is we're sort of making ourselves a list of questions. We're saying, what's the biggest element in this whole linked list? Not sure. But what I might do is I'll draw this a bit lower so that it's a bit clearer to see. In this whole linked list, I don't know. I'm not sure. Oh, happy little accident there. Pressed undo too many times. But we do know that we can try and find it by finding the answer to a smaller question. And the smaller question in this case is, what's the biggest element in this linked list? And so we draw ourselves another question mark, right? We're still not sure, but we've asked ourselves a smaller question. We're making some progress. Oh. There we go. And once again, we're going to sort of ask ourselves a smaller question. Ask ourselves a smaller question of what's going on in this section of the linked list. And finally, we ask ourselves what's going on with this null, the sort of empty linked list here. We've answered ourselves, we got to the point where we could answer the smallest possible question, which was, what is the largest number in an empty linked list? The answer in this case was -1, which is what we're calling sort of the, excuse me, that's what we're going to call the, a linked list which has no elements in it. We're going to say, well, that's going to be -1. Going to go -1 here. And then the point of us going back outwards again is because we've got all these question marks that we now have to answer. We now have to answer the question of, well, what's bigger in this sort of slightly bigger linked list? -1 or 7. And so we can go in here and we can say, well, now we know, because we got that extra piece of information from that smaller problem, it's 7. And then we can work our way back out even further. And we can say, well, we got the answer for our smaller problem with the linked list that started with 7, but what's the answer when it's 4 then 7 then null? And we can answer that question. We can say, well, the answer here is going to be 4. Oh, excuse me. The answer here is either 4 or 7. And given that we know that 7 is bigger than 4, or we can say 7 is the biggest element in this slightly larger linked list. And then we can work our way out and answer the final question, which is, what is the largest element in this entire linked list? The answer to which is 7. because it's either going to be the largest thing in the rest of the linked list, which is 7, or it's going to be 1, and 7 is bigger than 1, so we say it's 7. So we've worked our way back outwards to go from, well, we started off with a big problem, we broke it down into smaller problems, and then we answered our smaller questions and we stepped our way back out again. Answered a slightly bigger question, then a slightly bigger question, then a slightly bigger question. There was another really great question in the chat, which was, could we recurse until we find the last node rather than dealing with that with the empty list? Mark's put a great answer there, which is basically we could do it that way, but then we'd have to have a special case for if the list was null, or we'd have to guarantee ourselves that we never got past a null list. So we use -1 as just sort of a symbol of like, hey, empty list, this is a problem, and because we know that -1 is smaller than any positive number, if we're guaranteed we've got a positive list, it just so happens to work out that it gives us the right answer at the end. So in this case, we start with -1 at the end of the list, but then we would sort of always find, if there was a 1-element linked list, that there was something bigger than -1. So with a 1-element linked list, we always get that element. So we always get 7 in this case. And Eleanor's question, so the sort of first, it's not so much a round as this sort of a drilling down. It's like you're getting to a smaller and smaller problem. And it's to find those, to break it up into smaller and smaller pieces. Excuse me. Until you get back out again to a larger problem. Okay. So now that we've done sort of that diagrammatic explanation, I want to go a little bit more closely into something that we noticed before the break. Let me switch over now to some code. So, if we go down to our print list function, you may recall that there was a difference between, yes indeed, Mark, I am. You may discover that there's a difference between the way in which we implemented our find max function and the way in which we implemented our print list function. Our find max function, first what it did was it checked for null, but then it recursed into the smaller problem. It tried to solve the smaller problem first and used that information to get back out into a bigger problem. What we see though is that print list starts with a where is it? Here we go. Print list starts by solving part of the problem. So it starts by printing out the current node and then says, I've solved the current problem. Now I just need to solve the smaller problem of printing out the rest of the list. And so they're in reverse order, right? So you print out your current value, and then we print out the rest of the list, rather than in the find max version of events, where we found out whatever the problem was with the smaller part of the list, and then we worked back out and solved the bigger problem. The reason that I'm emphasizing this is because it turns out that there's another way that we could print out the linked list as well. We could swap these around, and the order here is really important. So let's say that instead of calling print list after I used printf, I put that first. Let's see what happens in this case. So in this case, I'm going to call print list, and then I'm going to print out a current value. I'm going to save this now, and we'll compile it again. I'm just going to need to comment out find max here, because otherwise we've got two definitions of find max in the one file, which isn't allowed. Going to run DCC. And then I'm going to run /recursion. And what we've noticed is this really weird behavior where we've gotten almost a linked list that printed out backwards. So let's go back in and clean this up again, and then we can have a look at why it worked this way. If it printed out backwards, then probably we're going to want to change it around so that the arrow goes left rather than right. And we're probably also going to want to print an arrow every single time we go through this iterative process. And we're going to no longer need to have that new line, because the X is going to be at the start of the line rather than the end. let's compile this again and see what happened. DCC. Crazily enough, we've now got a linked list that's printing out in reverse order. We're printing out back to front. And that's really, really strange. It's really weird. So let's have a look at the process that made it work like that. So for each of these cases, we're going to put in a little printf. We're going to say, here we're printing out null. Here we're going to say printf printing out the rest of the list. I'm just going to put that right before the print list call. And then here, we're going to say printf printing out the current value, brackets %d. And I might just put in new lines both up here and down here. Head value, and then I'm going to comment this out, comment out, and comment out the printing F here. So instead of printing out the actual list, I'm just going to print out some extra information about what's going on in my program. Let's now compile this. DCC. Rayg was very fast and noticed I may have accidentally left out a semicolon here. So I will put that back in. I'll jump back into print list and I will then use DCC. There we go. We fixed the problem. Phew. Compiles. Let's now see how this works. So we printed out the rest of the list, printed out the rest of the list, printed out the rest of the list, print, print, print. And it follows this pattern that we saw earlier today as well, where we've called this function a bunch of times, and we've had a smaller and a smaller and a smaller and a smaller and a smaller list that we were printing out, and then we printed out null, and then we worked backwards. It might even be useful if I add in here a %d currently at, and then I'll put in head value. /recursion. So we can see we had the big list, which started with 1, and then we broke it down into smaller problems. And then when we printed out null, everything from there onwards worked backwards. It went from null to 5 to 4 to 3 to 2 to 1. Let's reverse the order now. So let's go back to what we had before, where we're going to put this at the bottom, and we're going to put this at the top. And for this, I'm going to also add in an extra printf that says printf finish printing list, currently at %d. Head value. Okay. Let's see what happens when I run this piece of code now. Let's step through what's happened. So we printed out the current value. The current value was 1. And then we said we're going to print out the rest of the list now. Currently at 1, we're going to print out the rest of the list. And then we printed out 2. And then we said we're going to print out the rest of the list. Then we printed out 3 and said we'll print out the rest of the list. 4 and then the rest of the list. And then 5 and the rest of the list. And once we got to the end, we then finished all of our work at once. We said we printed out 5, we printed out 4, 3, 2, 1, and we worked all the way back up, and we finished our problem. So we went from having solved none of the problem to having solved a little bit of the problem and just saying, please solve the rest of it. And we kept making it smaller and smaller and smaller until we had no problem left to solve. And then we just sort of backtracked and we said, we're done. We printed out, and we printed out everything. I'm going to jump back into diagrams again, just to sort of go through this in another way, hopefully to clarify it for people who might be still a bit confused about what happened. go into here. So let's jump down a bit further in this document. Can I make a new page? Where's the button to do that? Turn off finger drawing, and I can scroll down. There we go. So let's now draw ourselves the same list we had before. 2, 3, 4, and 5. That looks more like a Y. Let's draw it properly. So here's my linked list. Goes from 1 to 5. And we're going to step through what happened when we did this procedure recursively. We started off by printing out 1. And we said, okay, we've printed out 1. I'll draw that in a separate color. Printed out 1. And then we said, let's just print out the rest of the list. So we called print list again, but this time we called print list starting at 2. So we started here this time. And then we said, let's print out the rest of the list. So we printed out 2. And I'll draw that in as well. Printed out 2. And now that we printed out 2, we want to print out the rest of the list. So we'll jump back out here, print out 3. And so now we've got to 3, we want to print out 3, and then print out the rest of the list. And we're going to follow that process. We keep following that process for 4, and then for 5. And then eventually, we get all the way over to here, where we've got this null pointer in the corner. So this, and I'll just make this super clear, that it points to null. And since we're pointing at null now, the program said print out an X, and that's what we're going to do. And now that we've solved this smallest problem, we work our way back out again. And we say, okay, we've solved the smallest problem. And we just say, okay, we solved the smallest problem. We solved the second smallest problem. We keep solving those problems. We've done all the printing, so we're all done. And we jump all the way back out from the smallest possible list that we printed out, back through 5, then 4, then 3, then 2, then 1. And our recursive print is done. Cool. I'm going to take a moment to look through the chat, make sure there's nothing I've missed. Yes, it's worth noting that you could use recursion in pretty much any of the questions that we've shown you this term. It just so happens that most of the questions we've shown you this term are generally easier to do with a procedural approach, I suppose you'd call it. So just using while loops instead. But equally, there are some problems that we've shown you this term where a recursive solution is helpful, or in fact is shorter than any other solution you could possibly have. So, for instance, having a look back at VLab, where is it? I'm just going to revert some of the changes we made to this code. Go back to what we had before. If we go backwards, what we'll find is this printing out backwards here took about 10 lines. 10 lines of us to say, we're going to print out the rest of the list, and then we're going to print out this thing. That was about 10 lines. Doing this code non-recursively, so procedurally, would almost certainly take 2 while loops, or it would take a stack, and it would be much more difficult to write. So in this case, a recursive solution is actually much easier. Now that we're back at my code, there's actually one other small example I wanted to show you that's a similar style that looks at the same sort of problem. Looks at the same thing of we're going to do something recursively. And once again, what we're going to see is it's actually easier to do it recursively than to not do it recursively. What's this problem, I hear you ask? The answer is, this problem is freeing memory. So As you may recall from last week and the week before, when we use malloc, we need to make sure that we free it. And this whole time, I've had a function in this program whose sole job was freeing a list. Here we go. So we go through, we free a list, we keep a current node, we keep a previous node, and then we need to do this weird dance with the previous and the current node, and we free the previous. It's interesting, though, because we've got to deal with these two nodes. I know that some people find this quite confusing. Some people are like, oh, I've got to deal with the current node, I've got to deal with the previous node, I've got to move them all around. And it turns out that when we're using a recursive solution, it's actually, there's a simpler way of doing the same thing. Or at least there's a way which, with a little bit more thought, we can write a few less lines of code. So let's take a look at what that solution will look like. I'll jump back to my drawings. Let's now scroll down just a little bit further. Okay. So let's say that the list that we've got is the list that we saw earlier, which is 1 goes to 4 goes to 7, which goes to null. Now, if we wanted to free this list using the method that we've all seen, we'd have a head pointer. Head. We'd have a current pointer. And we'd probably also have a previous pointer, which in this case will start off pointing to null. Okay, so I've got my head, I've got my prev, and I've got my cur. Now, what I would do is I would first of all take a step forward, and I would say, well, let's move my cur node so it points to the next thing. I'll move my previous node so it points to cur. So let's draw those in. First of all, we need to move the previous node to point to cur. So we've got two nodes pointing at the same place. And then we would need to move our current node so it points to the next node. And then we'd say, well, okay, we've got a hand on both our previous node and our current node. I can free my previous node, but I've still got a grip on the current node so I can keep going forward and keep freeing more nodes. So I would then go in and I would use the big arrow of big red X to free this node. So I'd say free prev, and that would free that node. And I could follow the same process again. I'd say, well, let's now get prev to catch up to cur. So we'd have prev and cur would both point to the same thing. And then we'd say, well, okay, we need to move cur forward again. We'd do that. And then, now that we've got a grip on the next node, I can free prev. So I can say, well, I've still got a handle on cur. I can free prev. Let's do that. And I can keep going. I can follow this through a few more times. I would follow the same process to get rid of 7. And then by that point, hopefully, cur would point to null. And I'd know that I'm done. That's the process that we just saw written out in VLab. So in VLab, we have an n, which is the current node. We've got prev, which is the previous node. While n, which is the current node, is not null, we move the previous one to be equal to n, so they point to the same thing. We move n to point to the next thing, so whatever is after previous. And then we free previous. And we keep following that process. But there's another way of doing it. Let's rewrite this out now with a recursive solution. So, instead of doing this, we'll comment this one out. So, with recursive solutions, like we've seen already a few times today, there are a few questions that we ask ourselves. First of all, we need to deal with what's the base case. For a linked list, it's almost always dealing with head equals null. So let's do that. If head equals null, well, then what do we need to do? We have a think for a second and we can say, well, if I've got an empty list, if the head is null, there's nothing for me to free, so I can just return. Or alternatively, I can have an else case. So I could say down here, instead of return, I could say if and then else down here. I'm going to leave the return in here, though, because there's no... I don't want to leave this if statement empty, basically. So we'll just say if head is equal to null, then return. And then there are two other possibilities. I'm going to have to, at some point, call free list. And then at some point, I'm going to have to also free head. And the question is, well, which order do I do this in? Is this like some list where we need to answer a small problem first and then we sort of build back out? Or is this like printing where we solved part of the problem and then we broke it down into a smaller problem? Well, let's try it one way and we'll see if this works. So we're going to go free head. And then we're going to run free list head next. So we have a think about this for a second. And we say, okay. So we've gotten rid of whatever the current thing is. We try and free list. And then we're going to free head next. Oh, wait. Head doesn't exist anymore. Let's take a look at what happens if we were to run this in the terminal as well. Maybe we'll get an interesting error. Whoop, our linked list looks like malloc use after free. Oh no. So what happened here was we tried to free the current element and then we tried to free the rest of the list, but we didn't have access to the rest of the list. Now, the solution for this that we would have seen previously, that we can see up here, or down here, excuse me, is that we have two pointers. We've got a previous pointer and we've got a current pointer. And we say, well, if the current pointer isn't enough, we'll just remember wherever we used to be. We'll move forward one. We'll free where we used to be, and then keep going with the next element in the linked list. But there's a simpler way of doing things. If now we say free list head next, and then we call free, what we've done is we've said, well, the first problem, before we can free the current thing, is free everything after me, right? So if my linked list is 147, and I'll go back to that in a moment. Jump over here. So if I go back to what we had previously, I've got my head pointer. The first problem that I've got to solve is freeing the rest of the list. Before I free myself, I have to make sure that I'm not pointing to something that we need to free. And so what we do is we say, okay, first of all, free the rest of the list. And so we say, well, okay, that's fine. We're going to call free list starting with a new head. Instead of this being the head, we're going to have this be the head. And we have the same problem again, where we say, well, before we can free 7, I've got to wait until 7 is freed. I've got to wait for a while. And so we call free list again, this time on 7. So we go, okay, there's no... we'll call free list on 7, or head next. And now, this is head. Okay, so now we're pointing at 7. And once again, 7 says, well, I can't be free yet. I've got to free my next thing. And so we call free list of null. But when we do that, something different happens. When we call free list of null, if this is head, we've already dealt with that case. In that case, we just return. If we're dealing with a list that's got null in it and nothing in it, then we don't have to worry about freeing anything. And so we can build backwards a bit. So we can say, well, we've freed everything after 7. And so we go backwards and we say, well, 7's the head, but now we can free 7. We can get rid of 7 because 7 is no longer has anything that it points to. Let's cross that out. And then, now we've finished freeing 7, we go back to 4, because 4 made sure that we'd freed 7 first, and we'd say, hey, 4, we've already freed 7, now we can free you. So, here's my head. Well, now everything after 4 has been freed, so we can also free 4. Excellent. And finally, we get back to 1. And remember, 1 is what we originally called free list width. And if 1 is the head, and we freed everything after 1, well, then now we don't need to worry about anything else. Now we can just say, well, okay, we'll get rid of 1. And we've returned an entirely freed list. Entirely freed. We'll go back into VLab. And so what we notice is when we're looking at VLab, oh, hey, look. We've written an entire program, or an entire function, which frees a list with 4 lines of code. No, 5 if you count the curly bracket. But we've said, well, if we're at the end of the list, do nothing. It's easy. Simple case. Otherwise, free the rest of the list, and then free me. And because this problem has sort of been broken down in smaller sections, by the time we get to the point where we free head, we've already solved the problem of having freed the rest of the list. So we didn't even need to define extra variables here. All we needed to do is we need to say, cool, we're going to free head. We're going to free everything after head, and then we're going to free head. Okay. I'm going to jump back into my slides for a moment, just to jump on this point. So one of the benefits of recursion that we've already seen, I need to change what my slides are showing. One of the benefits of recursion that we've already seen is that we can do things both forwards and backwards. So we were able to print out a list forwards, but we were also able to do it backwards, just depending on whether the recursive call happened before or it happened after I did whatever other work I had to do. So in the case of that print list function, if I printed before I called print list, then I would print it out forwards, because I'd print out the first thing and then print out the rest of the list. If I had the printf after I called print list, then what would happen is I would print out the rest of the list first, and then the last thing that would happen would be I print out myself. We'd print out backwards. That's one of the really useful benefits of recursion that we've just seen. The other one, which I will jump forward on slides 2, is that there's no need to have a previous pointer in some cases. Because we're calling functions inside of functions inside of functions, we can actually make our problems much simpler. We don't need to remember what the previous element was. We don't need to remember anything else about our linked list. We just remember we're at the head, and we can deal with something after the head, and then we can deal with the head itself. So I'll jump back into VLab now. I sort of had 2 different ways that we could end this tute. There was one problem which we might not do given the time that we've got. I'll first of all have a look through the chat, make sure there's nothing I've missed, and then we'll look at one more small recursive problem, and we'll finish up there. So I can see, first of all, I'll note that we've apparently all just received an email regarding the issues with the service of CSE services, which is good. So I'd recommend you have a look at your account. 151 will probably also release an update sometime later tonight once we've figured out exactly what's going on there. And if there are any extensions or that sort of thing, we'll get in touch with you over the next few days. If you've got any questions, once again, you can contact the course to be able to get in touch with us about that. So, anything else that I've missed? Excellent. Okay, cool. So the last problem that I want to look at is something that's going to work on both before the list, printing out before and printing out after we do a recursive call. So in other words, what I'd like to do is just sort of show you how recursion looks in a very visual way. We're going to do this by starting with the print list function that we've already got. I'm going to make one change to it though, which is I'm going to tell it how many elements we've printed out so far. So int how many elements printed. So when we call this function, I'll just go and edit the prototype at the top. So print list, where is it? We'll copy this up here. Nope. Typo. There we go. So how many elements have I printed so far? I'm going to jump down to yeah, I'll happily touch on that problem at the end. I just didn't want to jump into it because I'm not sure that we'd be able to get through the whole thing in time. So, how many elements printed? We'll jump down to where we called print list. When we called print list for the first time, we've printed out 0 elements. So we're just going to say, well, we've printed out 0 elements. So we're going to hold on. We're going to start off with how many elements printed equals 0. We're going to make a slight change to how our program works. We're going to put it back in order so that it prints out before calling print list. And we're going to change the arrow direction accordingly. So here we're going to print out the first number and then the second number and then the third number and so forth. So we're going to print it out in sort of forwards order. But what I'm going to do in here, because this is a function, I can add in pretty much any code that I like. I'm going to add in a very brief while loop, which says int I equals 0, while I is less than how many elements printed. I'm going to put char a space. And then here, what I'm going to do is I'm just going to change it so instead of printing f an arrow beforehand, or afterwards, sorry, it prints out beforehand. And of course, what you may have noticed is that I forgot to put an I++ in my while loop. So now I've got a while loop, which is going to go from 0 until however many elements I've printed. The other thing you'll notice that I've forgotten to do so far is that there's one called a print list that doesn't tell me how many elements I've printed. And so I'm going to edit that as well. I'm going to make sure that we say, well, we've printed out how many elements printed plus 1. This is a really common thing that we do in recursive functions, where we actually pass in a value to the inside problem. And what this means that we'll be able to do is we'll be able to see almost how the computer looks at this problem in terms of breaking things down into smaller and smaller parts. So let's now compile this function, compile this code. Oh, I might also just put in a new line here as well, excuse me. Compile again. DCC. What we can see is that we've sort of every time we've printed out 1, and then we've gone to a slightly smaller problem. We printed out 2, slightly smaller problem, 3, and then 4, and then 5. And this is showing us what our computer is doing internally. It's showing us that internally, the program tries to solve the 1 problem, prints out 1, and then it says, okay, now I've got to solve the rest of the problem. So it prints out 2, where it calls print list with the first element being 2, prints that out, and then tries to solve a smaller problem again. It tries to solve printing out 3 and then the rest of the list. So it prints out 3, tries to solve a smaller problem, prints out 4, and then smaller problem still, and prints out 5. So this is the exact same code that we wrote before with a linked list. I just wanted to make the point here that what's happening is this sort of every time we're solving a slightly smaller problem. And then at the end, what happens is all of our sort of print lists finish at the same time. They finish the most internal one, and then it finishes the second last one, third last one, fourth last one, and jumps back out again. Okay. Interesting to note, we could also do a very similar thing, but move the print list up. Do that. We'll save this, and we'll run it. Now what's going to happen? Oop, what did I do wrong there? Excuse me. I have to move this up even further. Ooh, what's going on here? My VLab is not very happy. There we go. So we're going to call print list before we do anything else. And now, hopefully, if we save and compile, we've solved our problem in the opposite order. We started with the smallest problem, and then we worked our way back out. We solved 5 first, and then we printed 4, and then 3, and then 2, and then 1. Okay, cool. I'm going to jump back into my slides now. We're approaching the end of the lecture. I want to talk very briefly about the problem that I put at the end. And then I'll hand back over to Mark to just sort of do the final words for the lecture for today. There's this last example that I wanted to talk about. This is an example of a linked list. And the problem that we wanted to solve was find every possible way that we could sum a linked list together. So that would have involved us, maybe we don't include any elements in the sum. So it's just 0. Maybe we only choose the first element. So we sum the first element, but none of the other ones, which is equal to 1. Maybe we sum the second element, but not the first or the third. Maybe we sum the first 2 elements together, but not any of the others. Or maybe we add them all together. And what if I wanted to figure out every single possible sum of my linked list? Now, there's going to be a lot of them. Those of you who have done some more mathematics might notice that this is an exponential problem. So it's going to be 2 to the 3, I believe. We've just pointed out that no, we don't have all of the possible solutions in here. I should have 2 extra ones. I should have, I should have 1 plus 7, or I should have 4 plus 7. I have accidentally left those out, which is why it's so nice sometimes when we have a program to do this rather than us doing it as humans. This program can tell us when we're wrong. And what we'll notice here is that this problem breaks down into at every step deciding to either include or exclude a particular number. So either we say we're going to include 1 and we're going to solve for the rest of the list, or we're going to exclude 1 and then figure out all the possibility for the rest of the list. And what we notice is this could be solved by having 2 recursive calls. We call find every sum once including the first number, and then we call it again excluding the first number. And then we break this down into a smaller problem, and the smaller problem we're going to solve by including 4 or excluding 4. And each time if we call let's say it's find every sum twice, the first time we'll call it twice, and then each of those 2 times we're going to call twice again, so we'll get 4, and then each of those 2 times we're going to call it twice again. Given the time, I'll leave it as an exercise to you all to see if you can figure out how would you call the function twice rather than once. But what you might notice is that it turns into almost like a tree. There's a tree of we include a number or we exclude a number. Now, this is just touching our feet in the very surface of some interesting computer science problems regarding, I can see that there's some chat on, is this combinatorics? Is there factorials going on? Are there exponentials going on? This problem has 2 to the 3 solutions, as it turns out. But it very, very quickly becomes a very big problem. And it's an interesting problem in computer science as well. Is how do we deal with all these possible situations with decisions about do we include something or do we not include something? But here, once again, what we notice is that there are that using recursion would make this a much smaller solution than if we had to do it any other way. I'll leave it as an exercise to you all to maybe resolve some of those questions in chat about, is it 2 to the n or is it 3 factorial? Can we use recursion to solve this problem quickly? They say that you should always, finish your movie right before the big resolution so that everyone comes back wanting to find out a bit more. But here's an example again where it's a really problem where it'd be much more difficult for us to solve without recursion than with recursion. So let's now just return to what we've learned today. Right? There are 2 things I think that we've learned today that are really sort of big takeaways. The first one is we've learned sort of a new way about thinking of solving problems. Instead of solving a big problem, we can just solve smaller, easier problems and then build up based on those solutions. So at the start of today, we looked through that example of just walking through a linked list, and by the end of walking through the linked list, we had an answer to what's the biggest element. But instead, what we've learned now is, well, instead of finding the biggest element, we can find the biggest element in a smaller list, and once we've found that answer, we can use that answer plus the current element to solve it for the current linked list. And so this is it's a shift in the way that you may be thinking about problems. And the second thing that we will have learned is that this is a way to write shorter and elegant programs. So you may have seen that with freeing a linked list, interestingly, freeing a linked list took up only 4 or 5 lines of code using a recursive solution, whereas we needed to have maybe 10 lines of code with 2 pointers and moving stuff around in a while loop when we were doing it without recursion. So recursion can sometimes be a neater way of dealing with things, though often it's at the cost of requiring more time to think through what the cases are or think through what's going on. So I'm just going to look through the chat one more time, check if there's any last issues to deal with. There's a bit of discussion there about is it n factorial or 2 to the n. I can say that it is in fact 2 to the n because at each step you're deciding, will I include this or will I exclude this? So each time there's a decision with 2 options, in or out, on or off almost, and then you go through each of the different possibilities, and you can deal with sort of 2 times 2 times 2 different ways of summing up that linked list. I apologize that this set of slides didn't include those other 2 options, which probably would have resolved that issue. But apart from that, looking through the rest of the chat, there was an interesting question, which I'll answer very quickly, which was, could you do find max in the opposite order as well? I'm assuming what you mean was, could you find the maximum and then call find max recursively? The thing with find max that made it special was that we actually we needed to know the answer to what's the biggest element in the smaller list before we could answer the bigger problem. So when printing out something like a linked list, we could print out the current node and then print out the rest of the list, and that was fine. But when we were trying to solve that problem of finding the largest element, we actually had to work through and find the smaller node first, the smaller linked list's value first, and then use that in calculating the biggest value in the current list. Okay, cool. I might at this point, I'm going to stop streaming in about 10 seconds, so I'm hoping that Mark is ready to take over. You'll notice that the stream will cut out for a moment, and then Mark should reappear. My coup has apparently failed. We're going back to Mark now, but I will stop streaming in 5, 4, 3, 2, 1. Awkward silence.
All right, I think we're back on me now. Yes, we are. Just going back to the... Oh no. Hang on. Just going back. Okay. I have to turn off the stream, otherwise it feeds back into me again. So, just want to say thank you very much, Tom. It was really great to have you talking about recursion and stuff like that. I thought for me it was actually really interesting to be in chat and to be answering a lot of like little individual questions and stuff like that, which I think is it's just really interesting. There's actually a lot of different sort of methods of teaching, which is about having the students do the sort of presentation side of things while I do the Q&A side of things. So it's like, yeah, I thought that was a lot of fun, very interesting. Can everyone give a round of applause to Tom? It's pretty tough to do that for the first time, but I think that the nice way of you getting to do that in the first time with on a live stream rather than having to stand in front of a few hundred people, I think that can be a lot more daunting when it's in person. But anyway, thanks Tom for that. So just to clarify for everyone where recursion sits in 1511, and we talked about this a little bit in chat, is that we can use recursion to solve a lot of the same problems that we've already been doing. We can use our procedural program, procedural's not exactly the right term, but close, as in the line by line, just go through from top to bottom way we've been doing things to solve all of the same problems as well. The deeper you get into the computer science and the more complex things get, the better it is to be able to do things in different ways so that you can apply certain solutions to certain problems. It will become more obvious with a bit more practice. So I'm happy for you to treat this learning about recursion as being something that is like, let's just file this away for the future. Don't have to use it now, but it's something that could be used in the future. If you're keen on it and you think it's an interesting thing to do, I encourage you to get some practice with it. So you can actually take a lot of the questions that we've asked about linked lists and do them with recursion instead of just looping through the list. So if I say take any of the lab exercises from this week, last week, maybe the week before as well, and don't use any while loops, and see if you can still solve the same thing using these techniques. That will be helpful practice for the future. We're not explicitly going to be testing you on recursion in the exam unless you consider that you want to use recursion in the exam to do things, or you look at a question and you say this is going to be easier with recursion than it would be with procedural programming. You can do that if you want. But it's up to you. And I should also say that the entire exam and the entire second assignment can be finished without recursion, which is why this is at the end. So the other thing I wanted to say is that this is the end of the kind of formal introduction of new topics that we're doing for COMP1511. So from here on, there will be no new content provided for 1511, but what we're going to be doing next week, I mean, next week is still valuable, is we're going to be talking about the assignment. So sorry, not the assignment, the exam. So we're going to be talking about what's in the exam, exactly what the kind of difficulty scaling of the questions are, what the kind of topic material is in each of the questions, as well as it's sort of just a general approach. So what we want to do is make it so that you can understand how you're going to approach the exam without getting kind of surprised by the exam the moment you sit down to do it. Because that's not what we really want to do. We don't want this to be like a shock, the exam. We want it to be like, I am prepared for this, and so the exam will measure exactly what I know, rather than I got so surprised by the format of the exam that I didn't understand how I was supposed to order the questions and the way I was going to answer them or anything like that, you know? And the rest of what we're going to do is we're going to wrap up the entire course. So I'm going to go through all of the topics one by one and talk about what are the core elements of each of those topics, and hopefully that lecture will kick off your study, because it will be a recap of everything in the course and hopefully remind you of the bits that you do remember, or remind you of some of the bits that you don't remember and give you a chance to think about those. Okay, so I'm going to wrap up the lecture there. Thank you very much, Tom, for taking the lecture today and taking everyone through what can actually be a very, very twisty concept of recursion. I'm going to I'll go into break mode and I'll come back afterwards and answer any questions anyone has. If anyone wants me to go over some of Tom's code for recursion and answer it and stuff like that, I think Tom will still be around in chat as well. So we'll be back in just a moment. I'm back. You're welcome. Those of you who are thanking me for not necessarily being the one up there speaking today, but I'll take that as a thank you for the term, in a sense. I mean, this isn't the end. We've still got next week, but in a sense. So while we've got, I guess, some people still here. There's actually quite a few people still here. Does anyone have any questions? Would you like me to talk any more about recursion or anything like that? So, Sulux Kuptor is saying, sorry, I don't know if I'm pronouncing that properly. Just joined the lecture because I had a question about streams. How would you suggest we go about choosing which one to do? What sort of research? Someone did a talk where they were talking about these streams. Was it you, Tom? I remember it potentially being you. What I would do in terms of like, I think what you're talking about is choosing a major in your computer science degree, for example. What I would do for this kind of thing is I would take some introductory courses in a series of different topic fields. So I'm just spitballing, so one in artificial intelligence, one in systems level thinking, like operating systems and stuff like that, one in databases, one in networking, pick all these different kind of fields, one in security as well, that kind of thing, and say, okay, how much is this field really resonating with what I want to do in computer science? And if it is, then look further into what constitutes a major in that field, and then start thinking about, okay, that's a suggested path you can go through. I should point out that people are not necessarily being employed specifically on their majors. Sometimes with people's majors, they'll look at them and go, okay, yeah, there's something great there. But often it's like the completion of the computer science degree is the thing that the employers are looking for and stuff like that. But for you, it might be something where it's like, oh, this is something I'm interested in. The other way that people do these sometimes is they reach the end of their degree and they realize that they've done a major and they're like, oh, okay, I'll tick that off. But obviously you're not one of those people because you're looking at planning it in advance. So I think that if you're thinking about that, then look at some of the early things in that particular major. Have a look at the courses, but then don't lock yourself into it, because you can switch that major anytime you want. But don't lock yourself into it until you've had a look at it, and then you decide whether you want to continue in that or not. I think the first year and maybe even first part of the second year of your degree, there's a lot of flexibility there, and I think you should use that to see what the breadth of computer science is, and you'll find that maybe one or two subjects really inspire you and you go, okay, that's it, locking that in. Third year is going to be all of those topics, and then you can do that. But I think that active exploration of those things is the best way to approach them. Eleanor's asking, can we clarify the logic behind calling the function itself again? Yes, we definitely can. Oshray's there, and he's got a link to something. Okay, so Eleanor, let me maybe do a Microsoft Paint thing here. Okay, so when we've got our main function, I'm going to draw it like a stack, I guess. We've got our main function, and then it calls another function. So it calls this other function, and this is the recursive function. And the recursive function says, I'm going to work on stuff. So let's say, for example, I had a little linked list, like so. When I call the first recursive function, it gets given the whole list. But when I look at the whole list, I say to myself, I can't do all of this at once. I'm a simple function. I'm not necessarily going to do the while loop through the whole list. So this is the idea of recursion. So it stacks up these functions instead of trying to do everything in one function. So it says, look, I can handle one element, and then I'm going to call another function to deal with everything else. So this other function gets called, and it gets given this much of the list instead of the whole list. And it says, can you deal with that? And we go, oh, I can't really deal with that either. I'll call another function. I can deal with one element, though. I'll deal with one element, and I'll call another function. And it goes like that. Each of these is the same function. So if this is, let's say it was the function to reverse, was it reverse? No, it was find the biggest, right? So this is, I'm just going to call it biggest. I'm going to call this one 0. I'm going to start counting from 0. And this is also biggest. And it was called by biggest. This is number 1. This is also the same function here. And so what we're doing is we're calling the same function multiple times, but each time the function is called, it's like another copy of that same function. In the same way that if we have like integers, there's not just one integer. When every time we create an integer, it's a new integer, but they're all the same, but they can have their own values. In the same way that these are all the same function here, but each one is working on a different piece of input. So the only thing that's different about these is which input they're working on and who called them. So when biggest 2 returns, it gives its information back to biggest 1. And then biggest 1 returns, it gives information back to biggest 0. Biggest 0 returns, and it gives its information back to the main. So this is kind of like, in a sense, a diagram of the structure of the functions calling themselves in recursion. So it's the function calling itself is a little bit like the linked list having a link to another node of the same kind. It's a different node, but it's the same kind. So this is what this is. It's actually multiple calls of the same function, but each one has its own memory space and its own variables and that kind of stuff. And so this one, main calls it calls itself, but it's not itself again, it's a copy of itself that it's added on top of the call stack as such. And then after biggest 2 finishes running, it will return to biggest 1, 1 to 0, and so on. The same way that we were doing any normal function calls, but now with recursion, the complexity becomes this stack. So what we tend to get in a recursive stack is like, if I'm going through an entire linked list, there'll be a function call for every element on the list, as opposed to if I was doing a normal looping through where it's simple in the function calls, but complex inside the function itself. So what we can do with them, in a sense, is we can write a really simple function that only deals with like one element at a time, because each one of these is like, I'm only going to deal with one element, and then I'm just going to pass the whole rest of the list on to another function. And it goes right down until we get the one that's only dealing with these should have gone, sorry, these should have extended to the null. But it then gets to the point where we have one remaining function that's only dealing with a simple solution, then it starts returning and they cascade back through to give their information back. So hopefully that gives you a little bit more of a another look into the way that you can have the function call itself, but it's not the same exactly, it's another copy of the same function, which is what gets created. And it's all very much a timing issue of what happens in this function before it calls the next one, and then what happens in this function after it calls the next one. Because when you consider biggest 0, it's going to do its stuff first, and then all of the others are going to run before this thing runs stuff again. So whether it does something, whether it processes something before it makes the call to other functions or after it makes the call to other functions really changes how the behavior of the entire recursive stack, in a sense, will come out. So hopefully that's giving you a little bit more information. I haven't seen any more from Eleanor there, but hopefully there's some stuff there that's getting it closer to an understanding of this, slightly weird way of programming, considering what we've been doing the last 2-3 months. Lorenzo is Zulux. Okay, cool. Someone else is saying, Samixture is saying, when there are parallel instances of find max running, head has different values in each of those. So how are all of those values stored with just one variable named head? So Samixture, this should this diagram should actually help you a little bit there, that each function call is given its own head. So there's the head here, which is the head of the first list there. But then biggest 0 is probably going to have the same head, which is a pointer to this. But when biggest 1 is called, it's given a different head, because biggest 0 has already processed the first element, and it's saying, no, I don't need you to process the whole list. I can look at the first element. I need something else to look at the rest of the elements. So its head is a pointer to this. And then biggest 2 gets the same thing, where biggest 1 says, look, I can handle one element, but I need you to handle everything else. And it's like, cool, all right, I'll handle everything else. So each of these pointers here are all head pointers. I should probably have labeled them. So that's a head. That's a head. And that's a head. So the interesting thing that we're getting here, right, is there's now, in my current state of this program, which is not even finished because there's more colors of biggest that's going to get called here, each of them has its own head. Because as you see in the code, I'm just going to open the... Oh, this is just going to be raw text in HTML, isn't it? Where is it? Okay, this is why we have syntax highlighting. Actually, I'm not even going to go there. Not going to go there. I have to open everything up now. It's going to take a little while, so I won't bother. But each one of these has a head, which is the input that it's given. And so each one is going to give a head to the next one, but it's going to be different. Because each one says, no, I can deal with the first element. I'm going to call biggest, or it's like find biggest, I think, on the rest of the list. So the thing that gets passed into the next one, which it then calls its own head, is going to be a different element of this list right until we get right down to the end. And then that last one's going to say, all right, my head is null, I'm just going to return. And then they'll start returning back through the list like that. So there isn't one head variable. Each function has its own head variable. So remember, like every time we have a function call, it gets put on the stack and has its own memory space. So all of its own variables are its own. So even here, when this head and this head are pointing at the same element, it still doesn't matter. They're still not the same variable, because every variable that's kind of created inside a function is within its own curly brackets. So it just stays there and it only works there. Hopefully that helps there. Okay. Tom's already answered this. Tom's helping Ryan as well with the colors and stuff. So I think that's it. Oh, Halogen said, how is Chicken today? Chicken, how are you today? Oh, yeah. Do you want to say hello to people? Oh. She was happily napping on the couch there. So I think she's a little bit dazed and confused right now, but this is how Chicken is today. I'll put her back. Now she's a bit excited and she wants to come and play because I've woken her up. Okay, looks like that's it for questions. I'll just give it a second and see if anyone has any more questions. Feel free to type them in. Otherwise, actually, this is a very particular time where you can actually, if you want to, you can go through my videos from the third term last year, and then you'll see two different ways of seeing this. This I think is particularly useful because we're unlikely to have time in tutorials next week to talk about recursion very much. We will a little bit, but it won't be that much. So you're not going to get your usual two ways of viewing things. Like usually you'll see things the first way, my way, the way I present it, and then you'll see it the way one of your tutors presents it. And granted, all the tutors did learn, well, nearly all the tutors did learn from me, all of these subjects, but they still have their own way of teaching it, which is very good. I think one of the best ways to learn things is to hear two different people explain it in different ways, and then you get different subtleties and things. So you can do that if you want to go back and watch my lecture on it. It's not that different, we're basing it off the same content and we teach it in a very similar way, but maybe it'll help in the same way that doing a lecture and then a tutorial might help. Matthew is asking, a little bit off topic, but how many pointer layers have you dealt with in production? I'm thinking about. I'm trying to think of which projects were the worst. So it's not necessarily pointer layers, but depths of complexity So I've worked with systems that were like, so let's just say these are nodes and pointers, and the nodes have a variable number of pointers. And then some of them were like ending early, and some of them were going deeper and stuff like that. And then when you got something along the lines of a pointer to here following a pointer to there and stuff, then you have multiple levels of that. And it really depends on how you want to code to break your own mind on how deep you would go on these things. And then if there's internal structures in these things which also have pointers. But if you're talking about, maybe like we're talking about pointers to pointers. Oh, yeah, this is that, isn't it? Yeah. Pointers to pointers to pointers. Then you end up with that kind of situation. I generally stop at somewhere around 3-dimensional, because I can understand it still. At that point, I can understand storing the memory address of another pointer. That's something that I can do. Like it's a level of indirection. But then when you go, I'm storing the memory address of the memory address that stores the memory address of another pointer that then stores the memory address of the final object somewhere. I would nearly go as far as to say that if you have that in your code, then you need to rethink how you're programming. Because once you've gone to that level, what are your odds? Because if you're at that level of complexity just in one of your pointers, it means the rest of your code is going to be really full on. Because you have to have built some ginormous data structure before you... well, not just ginormous, but ginormously complicated data structure before you even need that level of indirection to be able to access parts of it. So if you do need that level to access parts of it, then maybe you've designed your whole data structure in a way that's kind of impenetrable. And so what you're going to get, I think, there is the big problem that you're going to get is that you won't be able to understand it once it reaches a certain level. Or worse, other people won't understand it if they can't modify it. Because generally we'll be able to understand our code a little bit better than other people. But the thing that you want is your code to be able to be used by other people, unless you're like really, really specifically in some kind of hyper-competitive solo programming thing. I think even in programming competitions you work in teams anyway. So yeah, I think that when you get to that level of weirdness, you may need to go back to this thing, take it to a whiteboard and say, our data structure needs some weird connections to make work. So maybe what I should have is like a parallel data structure which is simple, and what it's doing is something like this. These are going to have to be structs that contain links to these, I guess. Yeah, do something like that where you go, okay, this is a highly organized data structure that removes a lot of the randomness in this main data structure, because this main data structure was not put together in a way where every row was actually accessible. Heaps of the rows have empty elements in them and stuff like that. So maybe if we did something else, I'm just completely spitballing, making this up, but maybe something like that. And then this thing has a maximum of 2 dimensions, and it never goes into like needing to start at the top and going down or anything like that. But I'm not sure. I don't know if what I've drawn there actually means anything or has a genuine use. But this is the kind of stuff we do on whiteboards when we're designing really complex programs. So this is actually like, this is coming off the top of my head for the like game playing AI that I've built for things. I didn't necessarily use this blue data structure, but there were things like that had all these internal pointers going back and forth between things. So we'd potentially have like double-ended pointers going back and forth between different places when we realized in a game, when you're looking at different futures in a game, and you go, oh, wait, this state is the same as this state. We need to link them together. And then things change about our strategy because we realize there's multiple different ways to reach the same position, except they're different positions in our data. Weird stuff like that. Anyway, I digress. That's probably a lot more than you needed to know. But yeah, Tom's answer was 3, and I'm like, yeah, I'm okay with that answer. Tom, you've been asked what kind of tablet you use. It looks Samsung to me. Or at least it looked like an Android tablet to me, because I've used a lot of iOS stuff, and it didn't look like one of those. Yeah, and Matthew, what you're saying is like the most common 3-dimension pointer is a pointer to an array of strings. And the good thing about that one is it doesn't feel like a pointer to a pointer to a pointer. When you say a pointer to an array of strings, people are like, oh yeah, I can handle that. We've compartmentalized the cognitive load of that so that we can handle it. In fact, you could go a level deeper than that because of that compartmentalization. So I think I just ended up drawing a crazy picture here. By the way, anyone who's looking at this picture and freaking out, you don't have to understand, like, this tree structure. Yeah, you're gonna hit this tree structure pretty soon. Like, one course on from this, you'll see these kind of structures, and they're really cool, super useful. Not necessarily the multi-tree, and definitely not 2 data structures linking up data in different ways. You may have to get a bit further than that to get to these. Maybe advanced algorithm courses, 3rd year, that kind of thing. When you start doing these crazy individual linkages up between things, then, I don't know, that might be thesis into PhD kind of thing, where you start actually using this weirdness. So it's kind of like, a look into the future, which I think is like what we're thinking about now, because we're nearing the end of 1511, so the introduction to programming has happened. You have been introduced to programming. The introduction's not entirely complete, but you kind of know what's going on. So I think a lot of people are now thinking of like, where do I go from here? Noticing a lot of the questions are like someone was asking about majors before. Other people were asking about what subjects follow on from 1511. I think that was on Wednesday and stuff like that. So, and people are thinking, what programming language do I learn next now that I've learned a bit of C and stuff. So lots of interesting stuff to think about there. Yeah, and what Tom's saying there is like the kind of data structure that we're showing there is like very similar to like operating systems. So when you think about this could be files. So this one's a directory, and it has in it these subdirectories, and each one of these has a potential number of subdirectories. You don't know how many, and you're not specified how many. Sometimes it has no subdirectories, and so that's where this one ends and stuff. And then sometimes there's one way of looking at it through that hierarchical structure, or this thing is a set of bookmarks that get you to certain points into it, right? So you can do that. You can do this like multiple kind of series of pointers going through the same data set. Right. Tom saying learn Excel next. I remember doing that once where I was writing a program. I think it was for randomizing students in student groups, and there was certain criteria that like students with different majors had to be put together, so we had to have some from some major and some from the others, so that we get a nice diverse group for every random group that was created. And I got about 4 hours into like this really, really nice application that was going to like take in all of their names and some of their demographic information and stuff like that, and then randomize it. And then when I hit that point, that I decided, so we copy paste all of their names into Excel, and then we randomize the columns. And I was like, oh man, that was like a maximum 5-minute solution in Excel. And I'd spent a few hours trying to do this really nice app with this like really nice data entry and stuff like that. And it's like, you know what? Use the right tool for the task. Sometimes a spreadsheet is a very, very powerful tool for certain types of things. And doing everything programmatically was very much the idea of what we call functional fixedness, which is the idea that, like, you know, when there's a term people say, it's like give someone a hammer and everything looks like a nail. So it's this idea that people, if they've got a hammer, they just think, this is what the hammer is used for and stuff. And I fell into that very much so, where I was like, I'm a programmer, so I'm going to program my solutions to everything. And it's like, that's not really how the world works. If you can open up your mind to saying that, like, let's not think that Excel is not a powerful tool. It can be quite a powerful tool if you use it the right way, right? And like, it's funny because we look down on it, we go, oh, that's not programming, that's just a really simple thing. And it's like, yeah, but if you have a simple problem, then it's better applying that than it is to try to apply an entire software development lifecycle to a simple problem. Jennifer makes spreadsheets for your games. Yep. Totally. Yeah. Oh, and also, as Tom's saying, there's a whole lot of Python in the back end of this course. What is it, chicken? Oh, she wants me to go that way. All right, that's my cue to leave. The lecturer in charge has said I need to go play with her in another room. And I think the questions have dried up now because I'm just talking about writing Excel and things like that. And you've got a spreadsheet for course progression, Jennifer. I think that's a good thing to do, because if you don't have those kinds of things, then you might get mixed up in your prerequisites and how many courses you can do per term and stuff like that, and then end up in a situation where it's like, oh, I have to do an empty term because I've missed out this. I need to do this one prereq before I can go on to all the other things that I'd planned. So it's nice to have this kind of nearly what you call a dependency graph. Like one of these. You could do that in a tree structure as well. But anyway, okay, I'm going to wrap it up there. I'll see everyone next week. Next week we're going to start sort of finishing the course in a sense. We're going to start talking about the exam and wrapping up all of the topics in the course. So just want to say thanks again to Tom. That was really good, and also it's really kind of nice to see the content from the outside, because I don't usually watch my videos because I don't have that much spare time. So it's nice to see the lecture delivered by someone else. It's like, oh yeah, that's interesting. So this is the format. This is how 1511 is taught. It's very cool. All right. See you all later. Have a good weekend, and hopefully everyone who lost any of their files, go check your emails. There should be some information about getting restored. But please, if you have lost your files, please get in touch with us. Because if you did lose time to this, and like there's going to be plenty of people who lost a full 24 hours of their thinking and their planning and their coding to this, let us know, because we'll make sure that you get that time back at the end of the assignment as well. Alrighty. Yeah, Tom's going to organize it and send out a notice later. Alrighty. See you all later.